So here in the third example, we are going to perform a queuing simulation in a spreadsheet. And this example is from your textbook. And let us read the question and understand this system and what we are going to do. It says, in a simple single server queue, we assume an infinite calling population from which people enter our system. Now, my friends, at this point, I'm just going to give you some simple definitions because we are going to study queuing systems in our future chapters, and we are going to teach what is a single server queue and what is a calling population. But let me tell you that this is a very simple queue. There is only one server, so everybody would like to get service from that server. There's only one person. So imagine a hairdresser shop with only a single hairdresser. So there are not multiple hairdressers that can serve you. There's only a simple single hairdresser. And we are assuming an infinite calling population, which means outside the system, there are infinitely many candidates that can enter the system. So even in the hairdresser shop, we have thousands or millions of people inside it. There are still too many people outside compared to the number of people inside. So calling population is infinite. Calling population means the potential customers that can enter into that system. So we assume that the inter-arrival times of the customers and their service times are known, deterministic, and the service times are in minutes. And inter-arrival times are also in minutes. So the first customer, it does not have any inter-arrival time. So this means the first customer is just going to arrive as we start to observe the system. And the second customer is just going to arrive 2 minutes later than the first customer. So here you learn this inter-arrival time concept for the first time. What does that mean? So the people are going to arrive the system with some duration between each arrival. So inter-arrival time means the time between the consecutive arrivals. So the time between the second customer's arrival and the first customer arrival will be 2 minutes. After the arrival of the second customer, 4 minutes later, the third customer will arrive. So there is 4 minutes between the arrival of the second customer and the third customer. And when the third customer arrives, after 1 minute, the fourth customer will arrive, so on and so forth. So I think we have understood what inter-arrival times mean, and the service times. Service times are also given in minutes. So the first customer, when he or she arrives, is going to seize the server and it is going to get a service for 2 minutes. So the service for the first customer is going to take for 2 minutes. When the service is complete, after these 2 minutes, the first customer is just going to leave the system. And the second customer requires a 1 minute service time. The third customer requires a 3 minute service time, so on and so forth. So, and in this queuing system, we are going to assume a FIFO rule, FIFO service policy. So what does that mean? FIFO is the abbreviation for first in, first out, which means the customers are going to be served in the order of their arrival. Actually, there are other service rules that we may practice in different queues, but FIFO rule is a fair rule. I mean, if you are working in a hairdresser shop, obviously you would serve to your customers based on the FIFO rule. Otherwise, you would lose customers, right? Now, in the first part of the question asks us to create a simulation table. So by simulation table, we are talking about the spreadsheet application, and it is going to contain for each customer the arrival time, the time that service begins, the time that service ends, the time spent in the queue, and the time spent in the system. So we are being asked 5 things to record in that table. So when does each customer arrive? When their service starts, when their service ends. When their service ends, they are going to leave the system, and therefore the moment where each customer service ends is also going to be called the departure time of that customer. Then the time spent in the queue and the time spent in the system is also being asked by each customer. The final question is to calculate the average time spent in the queue and the system by customers. So we have 6 customers in this small size simulation application. If we basically calculate the time spent in the queue by each customer and the time spent in the system, then we can take the average of these 6 customers for each value, and then this is just going to be a simple performance metric of this queuing system. Now, we are going to do this in this table. So I think we are going to zoom in a little. And we have customers here, and the inter-arrivals times are just pulled from the table given in the question. And based on these inter-arrival times, I can calculate the arrival time of each customer, starting from time 0, which is the observation starting time. My first customer is just going to arrive at time 0, and the second customer will arrive at time 2, just in the end of the second minute. And the third customer is just going to arrive in the end of the 6th minute, because there will be 4 minutes after the arrival of the second customer, and the third customer is just going to arrive in the end of the 6th minute. So basically, we are calculating the arrival times by taking the cumulative sum of the inter-arrival time column, right? So 6 plus 1, 7. 7 plus 2, 9. 9 plus 6, 15. So by that, we will understand that the 6th customer is just going to arrive in the end of the 15th minute of this system. Now, in the next part of the table, once we calculate the arrival time of these customers, we also need to write the service time for each customer. And these values are also pulled from the table given in the question. Because the first customer is just going to find the server idle in the beginning, first customer service is immediately starting at time 0. And since the service time is 2 minutes, the first customer is going to complete its service in the end of the second minute. So at 0, the service starts. It will take 2 minutes. So in the end of the second minute, the service will end for the first customer. And the arrival time of the second customer is the end of the second minute. So this means by the time that the second customer arrives, the service of the previous customer will end. So therefore, the second customer's service can immediately start as he or she enters the system as well. And the service time will be 1 minute. In the end of the third minute, the service will be complete for the second customer. Then the third customer will arrive at the end of the 6th minute, and the service will start when he or she arrives, because even if the server is idle at that moment, a service of any client or any customer can only start at the time of the arrival, right? So before he arrives, the service cannot start. So we need to be very careful about these things. And the time service begins is the end of the 6th minute, and the service time will be 3. So in the end of the 9th minute, the service of the third customer will be complete. The service ends at the end of the 9th minute. Now we have calculated the arrival time of the fourth customer as the end of the 7th minute. Can we start the service of this fourth customer as he or she arrives? Unfortunately, no, because we know that according to the FIFO rule, the service of the previous customer must be complete in order to start the service of the next customer. And the service completion time of the previous customer was the end of the 9th minute. So this customer, this next customer, even if he or she arrives at the end of the 7th minute, must wait until the end of the 9th minute, so the server becomes idle and can serve to this customer, the fourth customer. So you see, the time that the service begins for the next customer under the FIFO rule in a single server queue is what is the maximum of the arrival time of that customer and the time that the service ends for the previous customer. So in each value here is basically calculated by the maximum of 2 and 2 here. So this 6 is calculated as maximum of 3 and 6. This 9 here is calculated as maximum of 9 and 7. and this 11 here is calculated as maximum of 11 and 9, and this 15 here is calculated as the maximum of 12 and 15. Now, after we can determine the time that the service begins for a customer by adding the service time, the service duration to that customer the service beginning time, we can calculate the service ending time, and by this chain reaction, we can calculate the time that the service begins and the service ends for each customer. After doing that, I'm just going to zoom out a little. We can calculate the time spent in the queue by each customer. Now, how can we determine the time spent in the queue? By looking at the difference between the time that service begins and the arrival time. And the first customer, the second customer, the third customer, so they are just going to have 0 time in the queue. Their service will immediately start at their arrival. However, the fourth and the fifth customers are going to wait for 2 minutes because there's a 2-minute difference between the arrival time and the time that their service begins. So they are going to spend 2 minutes in the queue. Again, the sixth customer is not going to wait in the queue at all. And the average of the time spent in the queue will be 0.67. And the time spent in the system can be calculated as the difference between the arrival time for each customer and the time that service ends, which is also called the departure time. So if you check the difference between the arrival time and the time that service ends for the first customer, there's a 2-minute difference, and therefore we will say that the time spent in the system is going to be 2 minutes for the first customer. So we can calculate the time spent in the system for all customers like that. Or another way is what? You can basically sum up the service time for each customer with the time spent in the queue. So this is much easier. 2 plus 0, 2, 1 plus 0 is 1, 3 plus 0 is 3, so on and so forth. So after doing that, we are going to answer our first question by taking the average of the time spent in the queue by all customers and the time spent in the system by all customers. So in this small size simulation, we can say that a statistical estimate for the time spent in the queue in the system by the customers is 0.67 minutes, and another statistical estimate for the time spent in the system is 2.83 minutes. Okay, so these are basic performance metrics to measure the efficiency of this queue in the perspective of customers. Now, we have created a spreadsheet simulation here. Now, in the second part of this question, it asks, consider the number of customers in the system as a state variable, which means when we take a snapshot of the system at any second, at any minute, and basically we are working minutes in this example, at any minute when I take the snapshot of the system, I can basically count the number of customers inside that system. Now, which events are changing the state variable? So how can the number of customers in the system change? So if you observe a new arrival or if you observe a new departure, in that case, the number of customers in the system is going to change. So the arrivals and departures are going to be assumed as events in the system. The question asks us, create a table that gives the chronological ordering of these events. So we are going to observe 6 arrivals and 6 departures in the system, right? So when do we observe the arrivals? At minutes 0, 2, 6, 7, 9, and 15. And when do we observe the departures? In this column, the time service ends column, we observe at minute 2, 3, 9, 11, 12, and 19. So according to these values, we are going to create the chronological of these events, and we will say that at time 0, we will observe an arrival, which is the first customer. By the way, the customers are the entities of this system. They are the objects of interest. They are moving through the system, and they are the objects of the interest. And the arrival of the first customer or the first entity is at time 0. And the second event occurs in the form of a departure. Okay, the first customer departs at time 2. And at time 2, there is also another event occurring, the arrival of the second customer. and the second customer departs at time 3, as you can see. So the chronological order can be obtained by putting these values into a non-decreasing order, and then you are going to identify at which time which type of event is occurring and to which entity it corresponds to. So for example, let's check this event: arrival of the fifth customer at 9. So at 9, the fifth customer arrives. The next thing that happens is the departure of the fourth customer, and the departure of the fifth customer is the next event that happens. So once we create this table of events in the chronological order that can change the state variable, which is the number of customers in the system, then we can answer the last part of the question. Show the behavior of the state variable over a plot diagram where the horizontal axis represents the time and the vertical axis represents the state variable. We are going to draw this plot diagram. It says horizontal axis represents the time. So let's do that. So for how many minutes we are observing this system? The last customer is going to depart from the system at minute 19. So over the horizontal axis, I am drawing a time axis for 20 minutes. And I'm just going to observe the number of people in the system, number of customers in the system for 19 minutes. Okay. Now at time 0, I start with an immediate arrival. Therefore, there will be 1 people waiting in the system. For how many minutes? For the departure, until the departure of the first customer here, the next event, which is going to change the number of customers. So this first customer is going to depart from the system by the end of the second minute here. So here, the second minute is somewhere here. However, in the end of the second minute, there is also another arrival. Therefore, the number of people in the system does not change. So at the same moment, a departure and the arrival occurs. But in the end of the third minute, a departure of the second customer will occur, and the number of customers in the system will be reduced to 0. And this is just going to continue for 3 minutes, and in the end of the 6th minute, an arrival will occur, which is the arrival of the third customer, and the number of customers is going to increase to 1, and another arrival occur at the end of the 7th minute, and the number of customers will increase to 2. And this is just going to continue for how many minutes? It is going to continue for 2 minutes in the first place until the end of the 9th minute. A departure will occur for the third customer. However, at the same time, the arrival of the fifth customer will occur as well. Therefore, the number of customers in the system does not change here. But when, in the end of the 11th minute, the departure of the fourth customer will occur, the number of customers in the system will be reduced to 1 again. And again, in the end of the 12th minute here, the number of customers will be reduced to 0 because the fifth customer will depart. And in the end of the 15th minute, the arrival of the sixth customer will be observed, which is going to stay in the system for 4 minutes, and that customer is going to depart from the system at the end of 19th minute. So the rest of the plot diagram we cannot draw because we only observed 6 customers in the simulation. Actually, this is a small-sized example. In practice, we perform such a simulation for a very, very large number of customers to learn about the steady system behavior of that queuing system, but we are going to practice all of these in the following weeks anyway. All we want to do here is how we can create a spreadsheet simulation for a queuing system if we are given the inter-arrival time and the service times in a deterministic fashion, and then how we can give a list of the events that are happening, and based on the list of the events which are given in the chronological order, how we can draw the plot diagram of the number of people in the system. How can we draw the plot diagram of a state variable of this system? This was the main story of this last application.